by Robin Hudson, and is a generalization of the Heisenberg equation. So you know that in quantum mechanics there are two types of evolution. Well, I may there. Yeah. Because one is Schrödinger equation. One is a Schrödinger equation that you can write in the form. This is a Schrödinger equation in the operator language. So let me say a few words. I mean, this is because I know that many people in the audience are not physicists, so they maybe are not familiar. But this is, I will try to explain very shortly in mathematical language. So the usual Schrödinger equation is given on the wave function. Okay, so is this. Okay, and like every first order differential equation, it has an initial condition. So when I have t at time 0, this must be equal to the initial data. Okay? So what this is already in the 50s. Huckman gave a certain interpretation which led then von Neumann to prove the ergodic theorem. And the remark by Huckman was this: applied to the Schrödinger equation can be translated like this. Let us consider the operator ut that to initial data of this stochastic equation associates ut c 0, which is the solution at time t. And in functional analysis, there is a famous theorem by Stone that says that ut is in fact a one-parameter semiloop. Okay. And H is the Hamiltonian, which is a self-adjoint operator, and the exponential of a self-adjoint operator is given by the spectral theorem, which is well known in functional analysis. Okay? So, if you want to write the equation not for the wave function, but in operator language, you will have the following equation. And then, at time 0, you see, you have Ct equals C0. So it means that if you put ut at time 0, you get the identity operator, because C0 is additive. Yes. Okay. The identity operator, this is your identity operator, okay? Now, Heisenberg-Tasserati equation is a generalization of this equation, not of this. Of course, you can go back to this. But the generalization, you can do classical generalization, the classical stochastic Schrödinger equation, and you have not DUT, but because now you know Brownian motion trajectories are not differentiable, But you have D. Well, I think I continue. The language of stochastic equation is symbolic. Is D U T is equal minus I H U T and then plus D. You can have a coefficient here, and we can call it L. Here, L, D, and to follow notation of Professor Lucas, BT. And BT is classical Brownian motion. It's classical Brownian motion. Okay?
Classical
Brownian motion. Brownian motion.
So let me interrupt.
This is the classical stochastic Schrödinger equation. The Hudson-Bartasarati quantum stochastic Schrödinger equation. And you see, when you perturb with the stochastic term the evolution, where the coefficient of the perturbation is 0, you find the Schrödinger equation. But who tells you that the solution of such equation is unique? You can do the calculation. This is a nice exercise. You do and look for the Ito formula, use the standard classical Ito formula on the equation that I have wrote here. Let us call it equation 1, and find the condition of L which guarantees that the solution is still unitary, because you want unitary operator, because you want preservation of probability. See? The Hudson-Bartasarati quantum stochastic equation keeps account of this solution, of this problem that I pose, and so they write D, U, T. I write only the diffusion part, I don't put jump. Jumps is more complicated, and you have seen in the book, Professor Buca's transparencies. But I take the simplest case, the diffusion case, and it is like this. Du is equal. I write here the Hamiltonian part I will write for the last one. So this is the condition, you see. L, which was one of the fundamental discoveries of Hudson-Bartasarati, is that there is a bridge to guarantee unitarity. Of course, this must be multiplied by UT, and the initial condition is the same. The important discovery by Hudson-Bartasarati is that in order to guarantee the unitarity of UT, the coefficient must, there is a bridge, there is a connection between the coefficient of the martingale term, these are the dA and dA daga are martingales, and the drift. You know, the dt term in a stochastic equation is called the drift. So they are not independent. the dissipative, you see, the drift has two parts. In the Hudson part, this is the famous formula of Hudson and Baltasarati, in which you see the two parts of the drift. This is positive, and it is responsible of the dissipation. And this is the Hamiltonian term. So when the noise is zero, you put L equals zero, you find that's the cushion.
Okay. So that this is only true for time-dependent Schrodinger equation.
You see, the Schrodinger equation, in this, in fact, this is a nice comment, because it has some, but this has to be, to explain this, we have to go a little bit more into physics, because this U here is not precisely the U that stationary is Schrodinger. It is the U that comes in something that the physicists call interaction representation. And to explain what it is interaction representation, essentially interaction representation means that you have not, this is called the total Hamiltonian, but you have another Hamiltonian which is called the free Hamiltonian. Yes, typically in the physical literature, H0 is the free Hamiltonian. H is equal H0, which is the free Hamiltonian, plus some potential. Okay? In the physical literature. So when it is very useful, and this is very much used in quantum field theory, in the master equation, in the theory of open system, that you want to study the so-called you define a two-parameter object. Well, in fact, let me write that. You define, let us consider the time dependent. Let us consider ut, not ut, vt, by well, no. Because I have used u for this, so I have changed the notation. We consider vt is by definition ut and u0 minus v. So this means you go first, you go back with the free evolution, and then you go forward with the interacting evolution. Okay? So this is minus. Then, if you take the derivative of this Vt, what you see? You find that this is E, is U. You write the Schrodinger equation in the for U as we wrote like this, the operator equation. So we have minus H, minus IH, and UT, and you multiply U0T. I am applying to the Leibniz rule, because now this is the deterministic equation, not stochastic. So I can use it without autocorrection. So, and here I have this free semigroup, which is H0, but it has the minus sign. Yes. So here I have minus, and here I have plus, and here I have plus I, and H0 of U0 minus T, like this. And here I have UT, because I have applied Leibniz rule. So you see, here I take the derivative of this, which is this, and I multiply by this. Then I take this, the first, and I multiply by the derivative of it. Okay? Now, what happens? Now what happens? Oh, wait a moment, I have here in the free evolution, since H, this term, I can write, remembering that U0 minus T is equal E I T H0 with, so it is a function of H0, so commutes with H0. So I can put on the right this, and it commutes with H0, and H commutes. So I can also write H commutes with U for the same reason, because U has this form, it's a function of H. So every H commutes with every function of H. Okay? So this I can write UT U0 minus T times minus H on the right, times minus IH on the right, and this I can write the same UT U0 minus T that multiplies what? Plus IH0. Now what happens? Now what happens? Look, you have this, but this is by definition VT. By my definition, this and this is equal to VT. So I have equal to VT that multiply H. What is H? H is H0. Sorry, mu, I wrote mu. This is H0, the free Hamiltonian. H, I don't know, H0 plus, well, you can write V, but in Hamiltonian language we often write H interaction. Okay? There is free Hamiltonian interaction Hamiltonian.
So this V is not strictly a potential.
Is not strict. Well, it depends what you mean by potential. This includes the application to quantum physics.
What I mean by potential?
Potential is in finitely many degrees.
Oh, okay.
But if you are working, for example, in the theory of open systems, you typically have a small system interacting with an infinite dimensional system, quantum physics. And so this is the better limitation. This is better. Okay? So H is H plus this Hi. And there is minus I. Is Hi plus H0. I permuted them because addition is coming. And here I have, and here I have the minus sign. And here I have the same VT, but now with the plus sign. And there is I here, and here. And I. So you see, the free part is cancelled. And it remains indefinite. So roughly speaking, this is the idea. that you write an evolution not for the full Hamiltonian, but for only interaction. This should be done, the calculation in a more precise, in a fuller way, and you will find that HI will depend on T. And HI is precisely the free abode of HIT will be the free abode of HI. But I consider the case in which everything commutes, in some sense, is trivial physical case, but it gives you the feeling of what does it mean interaction representation. Interaction representation means that you essentially consider the evolution only the part which is directly responsible of the interaction. You, in some sense, forget the free. Okay? So this is the action. It's not a direct Schrödinger, but Schrödinger in interaction representation. Okay.
Sir, I have a question.
You can, what, tell me.
Thank you very much, sir, for the explanation. But from my observation, my little interaction with the literature in physics, I observed that people in physics, perhaps they are so conservative, they remain with the Schrödinger equation. With all this rich formulation, are they really seeing this as being canonical? Because people in physics, they prefer the Schrödinger equation. All these are the Boosting and Patasarati formulation. They hardly...
This interaction representation was not invented by us on Patasarati. This is standard in quantum field. All quantum field, let me do the calculation in a slightly better way. Let me say D with, let us say,
So we can use the other part of the board.
Is this clean?
We can use the other part of the board.
that is, well, but I want to...
You want to use the content here?
Yeah, so let us do the calculation like this.
That is like example.
Here, instead of using this commutativity, because the commutativity of HSD, I will use this. I will use that. dt of dt is the first I take, I leave as it is. The full Hamiltonian. I will do this calculation another time. Now, I want to say this to answer to your question. This interaction representation was famous in physics 50 years before Patasarati. And the reason why they do this is because in quantum field theory, you have, when you write the Feynman integral typically, you have, in reality, you always start with this solution, which is this equation, let me write, dvt equal minus h minus I, h interaction t multiplied by dt. And h interaction t is a minus I h0 hi. Bringing this, you will find a trivial limit. So
there is no time evolution.
There is, of course there is. But it's time evolution in interaction representation, which has the advantage that it makes this separation of the time scales. The whole theory of this stochastic limit, essentially the first stochastic, essentially is based on the following fact that you have the interaction Hamiltonian depends on lambda. In the simplest case, which is called weak coupling limit, this means that it's lambda times another integral, and the lambda is small. And this is perturbation theory. And then there is another asymptotic in physics, which is called scattering theory. Scattering theory. This is perturbation small lambda, scattering large t. No, large t. Scattering is asymptotic, but asymptotic of what? Of the interacting representation. So E I minus I t h total E plus I t free. When you go with t go to infinity, this is what in physics called the scattering operator omega. Omega, and this is plus infinity, this is omega plus. So a very famous operator in physics is called scattering operator. So you have two asymptotic theories which are fundamental in physics. Small lambda, perturbation theory. Large T, scattering theory. What is stochastic limit? Combination of both. But non-trivial, because you want that T goes into T over lambda square, not lambda. Why lambda square? Well, there is a long literature that begins with Bogolyubov and go with Van Hove, and then with the stochastic limit, our contribution. It shows that if you, instead of taking lambda square, take any other power of lambda, either the limit is trivial or it doesn't exist. There is only one exponent of lambda. So when lambda goes to 0, t, the rescaled time will go to infinity and you get scattering. But lambda goes to 0, so small. So perturbation. Put together stochastic. The very surprising, and this is the hard mathematical part, is that you start with the usual Hamiltonian of this form. That is why you need interaction representation. But you have h which depends on lambda. So this ut will depend also on lambda, and you will rescale lambda to, you will rescale the time to t over lambda squared. What is the very hard part of quantum transfer? Essentially, stochastic limit is the only good deductive theory of quantum transfer. The surprising fact is that not only the limit can exist, let me call it U stochastic, but that is unique. This is, you see, it's very mysterious a priori. In fact, it's very hard. Unitarity proof is very hard. Because in perturbation theory, when you do perturbation expansion of a unitary operator, each finite term is not unique. But in the limit, in this limit, it is. In scattering theory, well, this is typically in you need very technical condition to have the scattering operator. Okay, but this is true in very general conditions.
So that n that appears, h,
What?
h subscript s equals
H?
1 over 2m v squared.
This is the free Hamiltonian in 1 degree of freedom. Momentum.
So would this 1 over m come from the spin? Would this be the spin?
1/2M.
1/2M. So that would be the spin of...
No, not what. M is the mass. P is the momentum. And this is the kinetic energy. One or twice the mass. That momentum square is kinetic energy.
I think that is what you used in the case of quantum finance. You used the energy representation in the case of quantum finance.
Yes, many people use this. So you see, this is, but there is a lot of things to be done and to be. The stochastic limit is rather deep. Yeah.
As I've not read your book on it. I said I've not read your book on it. The book on stochastic limits.
Well, you have.
I saw the soft copy before, but I don't have the hard copy. Even when I have the hard copy, I will use it.
Well, on the web you can download.
I can download, yes.
Many young people are very good to find the book on the web, and this is on the web.
Yeah, I have.
You have it. The last time you bought it.
Yeah, I have it.
Oh, yes. So please let's give Prof a round of applause. Because you can all see how robust the discussion is like. I mean, if you are here, if you have done anything related to all this, you enjoy what he's doing. Because he's able to pull everybody along in all the directions. And he gives satisfying answer to all questions. I mean, so he's one Nobel laureate that yes, I know personally. So we're going to have discussions this afternoon, but I don't know if he is able to still do it according to.
Is this not a discussion?
Well, it's a discussion, but
I've done a lot of
this is
discussion.
5:20. Yes, but based on where we started. Yes, I don't know. I mean, do you still have anything you want to discuss?
There are questions. The schedule is to finish the half 6, but if people desire, we can finish.
Okay, so what is saying that if you have
there are no
questions, okay, but if you don't have questions or you are tired, then we can stop. But
yes,
it's good to go if you have questions.
So that we can come early
Tomorrow.
tomorrow. Bro, he's used to it.
Well, I'm happy we are all enjoying him, and I hope we enjoy him for a very long time.
Thank you very much.
So we can stop here for the day then, so that you can all go relax. Then by tomorrow, please, our 9 must be 9. If you have not taken your breakfast, forget breakfast tomorrow.
If you don't come to take breakfast at 8,
please, if you get there at 8, yes, please. So we should be seated because there are people that are going to communicate with
people
us
that
online.
will present tomorrow.
And they shouldn't be waiting while we are eating. They are the ones giving us knowledge. So please, let our 8 be 8 for our breakfast and 9 be 9 for our school.